Good morning, students. In my last lectures, I had discussed with you the various sorting algorithms and hashing, that is a searching technique. Now in my class lectures, I had discussed with you what is a binary tree. We were taking the tree unit. So we have done the binary tree and all its traversals in order, pre-order and the post-order traversals. So next topic is now binary search tree, and it's very important topic. So today I will tell you that how to search from a binary search tree, how to insert the elements, and then how to delete. Okay. So first thing is like what is a binary search tree? So there is a difference between binary tree and binary search tree. So what is a binary search tree? What is the definition? Binary search tree is a binary tree. So first condition is that it should be a binary tree in which every node contains only smaller values in its left subtree and only larger or equal values in its right subtree. Like you take this example, suppose you are having this binary tree. Now you take this node. So all the values that are on the left side, that should be smaller than E, and all the nodes that are on the right side, that means this is your right subtree, it should contain the values that are either greater than E or equal to this. Okay, like alphabetically if you will see that C, A, B and D, they will come before E, so you can imagine they are lesser than E. So all the values here are lesser than E, and all these values like H, F, I, G and J, they are coming on the right hand side. Now consider any another node, like you take C. Now all the nodes that are on the left side like A and B in this left subtree, left of C, in the left subtree they are lesser than C, and a right one, that is D, is greater than C. So this is a binary search tree. That means the value stored at a node is greater than the value stored at its left child and less than the value stored at its right child. It would be less than or equal to. Now consider this one. Again, one example of the binary search tree. I have taken here numericals. Like you take this node 25. Now consider this particular subtree. In this subtree, all the nodes are here greater than 25, like 36, 30, 28, 38, 40, 48, 45, 50. Okay, and all these nodes in this left subtree, they would be lesser than this, like 20, 10, 22, 5, 12, 15, 8 and 1. So they are lesser than 25. So this is a binary search tree. Now take any another node, because it should be true for all the nodes. You take 40. Okay, that means all the nodes that are on the right side, they should be greater than 40. Now here take this one, you have greater than 40. Okay, in this right subtree you are having 48, 45, 50, they are greater than 40. Now take this one, on the left subtree you should have the value that is lesser than 40. So what is you are having? You are having 38. Okay, so this is also satisfying the condition of binary search tree. You take any another node, like I'm taking 5. What is 1? 1 is lesser than 5. What is 8? 8 is greater than 5. So this is your binary search tree. Again, I'm repeating, in this tree, the left subtree of every node, now here it is written every node. That means the left subtree of every node contains the nodes with smaller values, and the right subtree of every node contains larger or equal values. Equal means, suppose if you have you can repeat the values, and suppose you have to insert 25, so that would come on the right hand side. Where it would come exactly, that I will tell you in the next slide. Okay, now here before going to the next slide, here I want to tell you that suppose already you have created this binary search tree, and now suppose you want to search for, I'm taking 45. You want to search, this is also a searching technique. You want to search for whether 45 is present or not. If 45 is present, it will give you that it is present. If it is not present, we may insert that. Okay, so search for 45. So start comparing from the root node. Compare 45 with 25. 45 is greater than 25, so come to this point. Okay, you have to go to this, right? Now compare. Now here it is 36. Compare 45 with 36. 45 is what? Greater than or lesser than? It is greater than, so go to this side. Again compare. Now here it is 40. Compare 45 with 40. 45 is greater than 40, so again go to this side. Now 45 is what? Lesser than 48. That means it can be somewhere over here. So 45 is lesser than, you are going here. Now compare 45 with 45. You are getting this 45. That means just after 1, 2, 3, 4 and 5 comparisons, you are getting your element, that is your 45. Okay. And the complexity of this will depend the height of this binary tree. And if you are having n elements, the height of a tree is big O of log n. Height will be log n. So the searching will take big O of log n time over here. Now I'm taking one more example. Suppose you want to search for, I'm taking 11. Okay. Now again you have to start with the root node in a binary search tree. Compare 11 with 25. 11 is lesser than, you are going to this side. Now again compare 11 with 20, you will go to this side because 11 is lesser than 20. Now compare 11 with 10. 11 is your greater than 10, so you will go to this side. Now 11 is what? Lesser than 12, you will go to left side. But there is no node on the left side. That means 11 is not present, okay, in your binary search tree. But if you have to insert, you can insert your 11 over here. Okay, suppose the question is that if it is present, find out the location. If it is not present, insert that. So you can insert that over here. So 11 was not present over here. Okay, now next is that how to insert in a binary search tree. So these types of questions can be asked in your exam, like construct a binary search tree by inserting the following sequence of numbers. So you have to take all these numbers one by one in that sequence, in this sequence only. Otherwise, your binary search tree will be different one. Okay. So how to do that? What is the first number that you have to insert in your binary search tree? That is your 10. So make 10 as the root node, okay, of this binary search tree. So there is nothing to be done. Next is your 12. Okay. Now you have to insert 12. Start comparing from the root node. Whenever you have to insert in a binary search tree, you have to start from the root node. Then only you can reach to that particular location where you have to insert this particular number 12. Okay, now compare 12 with 10. 12 is what? Greater than or lesser than? It is greater than. So 12 should come towards the right side. So what we will do? We will make a right child of 10 and we will store 12 over here. Okay, why? Because 12 is greater than 10. Now take the next number 5. So this is very important. Again, you have to start from the root node. Okay. Don't start from here. Start from the root node now. Now 5. Compare 5 with 10. 5 is what? Lesser than 10. That means it should come towards the left side. There is no left child. So that means 5 would be inserted over here. Next is your 4. Okay. Now this was the binary search tree before 4. So I have to insert now 4. Now again start comparing with 10. 4 is what? Lesser than 10? Yes, go to this side. That is not empty. So here again compare. There is 5. 4 is what? Lesser than 5? Go to left side. So left child is empty. So that means 4 can be inserted over here. So 4 is inserted over here. Okay. So next is your 20. Again start comparing with 10. 20 is what? Greater than 10? Yes. Now 12. 20 is what? Greater than 12? Yes. Now there is no child node of this, so 20 would be inserted over here. Next is your 8. Start comparing from here. 8 is lesser than 10, go to this side. 8 is greater than 5, go to this side. So this is empty, so I can insert 8 over here. Just see, 8 is inserted over here. Next is 7. 7 is lesser than 10, go to this side. 7 is greater than this, go to this side. 7 is lesser, so 7 is inserted over here. Next is 15. I am taking this binary search tree to insert 15. 15 is greater than 10. Yes. 15 is greater than 12. Yes. Go to this side. Here still you are having 20. 15 is what now? Lesser or greater? It is lesser. So it will come to the this side. So 15 would be inserted over here. Just see this one, 15. Next last element is here 13. Now again start from here. 13 is greater than 10. You are coming here. 12 is there. 13 is what? Greater than 12. You are going here. 13 is lesser than 20. Go to this side. 13 is lesser than 15. So go to the left side. So that was empty previously. So 13 can be inserted over here. So this is your binary search tree. Now in this binary search tree, just see all the nodes. You take any nodes. Suppose I'm taking 10. So all the nodes that are on the right side, 12, 20, 15, 13, that is greater than 10. And all the nodes that are in the left subtree of 10, those are lesser. You take any another node like 5. So left side 4, lesser. Right side you have 8 and 7, those are greater than 5. So this is your binary search tree. So this is how to insert in a binary search tree. Next I'm taking the algorithms to insert. Okay, that algorithm will cover searching as well as the insertion. Okay, because whenever we have to insert, before insertion actually I need to find out the location where I have to insert that. So that would become the searching technique. Okay, here I have again for these examples, I have made one more binary search tree. This is 40, 60 you have to insert, 60 would come over here, then 50, 50 is greater than this, 50 is lesser than this, then 33, lesser than 40, then again 55, 55 greater than this, lesser than 60, greater than 50. So 55 is coming over here. 11, 11 is lesser than 40, lesser than 33. It's coming over here. Okay. So first algorithm over here is find. Find means searching. I'm going to search from it this suppose binary search tree. What is given, like I'm using the linked list representation, so info part left and the right of every node is given. Then the root means it is a pointer to the root node. This is your root. Here I'm writing, this is your root node. Item means the item that I want to search for. Suppose I want to search for 50 or 55, that is item. Location, so what is the location now? Location is the location of the element that you want to search for. That means if it is present, location would be, suppose I want to search for 50. So location would be the address of this particular node. But if that item is not present, location would be null. Now with that, I need, whenever I have to insert, suppose that element is not present. Here I want to search for, suppose 45. So 45 is not present. So what is location? Location would be null. But in that case, I want the address of its parent node. Okay. Parent node means कि 45 would be the child of this particular node. Okay. So it would be clear once I will take this. So this procedure finds the location of the item in this binary search tree P and also the location parent of the item. So there are three cases. I need to consider all these cases. Suppose if the location is null and the parent is also null, that means your tree is empty. There is no element within that binary search tree. Now, location not null, but the parent is null. So what's the meaning of this? Now suppose you're having a binary search tree in which you are having a single element 45. You are having a binary search tree 45 and suppose I want to search for this 45. So I will go to this node, I'll compare 45 with 45. Both are equal. That means the location is this. What is the location? Location is the root. So location is not null, but what's the parent of this? That is null. So parent null. That means इस case में क्या है? Item is root of the root this tree, binary search tree. Okay. Third case is if location is null but the parent is not null. What's the meaning of this? Suppose I want to search for, I'm again taking this. Suppose I want to search for 45 from this tree. I want to search for 45. Okay. Now I will compare 45 with 40. 45 is greater than 40. I will go there. 45 is lesser than 60. I'll go there. 45 is lesser than 50. Yes, I will go to this side. But this side is empty. That means you can say 45 is not present. What is the location then? Location is null. But what is the parent of that? Parent means if 45 had been here, what was the parent? What would be the parent? Parent would be 50. So PAR would be 50 over here. So that is very important, that if location is null and parent is not null, it indicates that the item is not in the tree, but it can be inserted. It can be added to tree as a child of what? As a child of PAR location. Okay. Suppose if I have to add 45, I would add 45 as the left child of what? 50. So I should know the address of 50. It's parent node. Okay. So this line is very important, what I'm going to do after this. Okay. Now this is the searching technique. Okay. So I'm taking some variables and initializing those. First of all, I'm taking the root. Okay. If root is null, that means in a binary search tree, if the root is null, root pointer, that means location is also null and the parent is also null. Why? Because that your binary search tree is empty. Okay. Next is if you're finding it difficult to find out what is written over here, this algorithm I have taken from your book only, Shom series book. So you can open that book and you can find out if anything is missing from this. So if root is null, set location is equal to null and parent is equal to null. Next one, next case. This was the first one actually. If location null, parent null, that means tree is empty, that I have checked. Okay. Next one is the example that I have taken. Suppose in a binary search tree, you are having a single element, that is your 45. Okay, this is the root. So I want to search for 45, suppose. So in that case, if item is equal to info of root, 45 is equal to info of this, yes. In that case, location is your root. Means location at which 45 is present. It is present at root. And what is the parent? Parent of that is none. Okay, there is no parent of that. So I would return from this. Okay. Now the next case is that neither this case nor this case. That means this case. That means item is not present, but the parent of that would be there. Parent is not equal to null. Like here, I want to search for 45. Okay, now this is important. I want to search for 45. So whenever I want to search for 45, I have to start with the root node. So here item is your 45. Info of root is what? 40. I will compare 45 with 40. 45 is lesser than 40? No, it is greater than this. If it is greater, just see I have written the else. That means if item is greater than info of root, what you have to do? I'm taking two variables, ptr. ptr would be initialized to right of root and save would be initialized to root. That means this was your root. So save will become, here I'm writing S stands for suppose now save, and ptr would be right of root. I want to go to right side. So one pointer I'm taking over here. Suppose here I'm writing P. P means PTR. So PTR is your would become 60 and save would become 40. Okay. PTR is right of root, save is root. This is just the initialization. Okay. Next. Next is that repeat steps 5 to 6 while pointer is not equal to null. Okay, now we are checking item is equal to info of pointer. What was your pointer? Pointer was pointing to this 60. So now I'm comparing 45 with 60. 45 is equal to 60? No, 45 is not equal to 60. So again I'm checking that 45 is lesser than or greater than. 45 is lesser than, compare this, 45 is lesser than 60? Yes. In that case, what you have to do, save would become pointer and pointer will become left of pointer. Okay, like in my case, now save would become pointer. So what was your save? Save now would be pointing to this one. Save would become this and pointer is pointing to left of this. So pointer would become this. P would become this one. Okay. Now again you are checking that while pointer is not equal to null. This one. Okay, save is becoming pointer, pointer is left of pointer. This is your loop, end of this loop. So again you are going here, you are checking while pointer is not equal to null. Is pointer null? No, pointer is not equal to null. Again you are checking with your item with info of pointer. You are checking your item with info of pointer. Pointer was your 50. Okay, you are checking 45 with 50. 45 is equal to 50? No, 45 is not equal to 50. So again you are coming to this point. 45 is lesser than or greater than? 45 is lesser than 50. Okay, so you will go to this side. Now this is important. Okay, so save would become now 50. So again I am repeating, save would become pointer. So save would become your 50 and pointer will become left of pointer because 45 is lesser than 50. So pointer would become your what? What is left of 50? That is your null. So here I am writing that would become your null. Okay. Save is pointing to this, pointer is null. So once your pointer is null, you will come out of your loop. Just remember this, save is pointing to 51. So here I will have to erase this, then only I can move to the next slide. Okay, now here. Now here, just compare your pointer is null. Yes, now pointer is null. You will come out of while loop. Okay. Before coming out of while loop, what you have done in save, you have stored the pointer. So after coming out of this while loop, you are saying your parent. Parent is what? Parent is your save. And what is location? Location is null. Why? Because we couldn't find the 45. So location is null. And in parent, I'm storing the address of what? I'm storing the address of 50. Because if I have to insert, I will insert 45 as the left child of 50. So I need the address of this 50. Okay. So again, I'm repeating just these things. First thing is, this is first condition, that is when your tree is empty. That means if root is null, both location and parent would be null. This condition is when the item that you want to search for is equal to the root node. Okay, in that case, location would become root, parent would be null. This thing is for the initialization of PTR and save. That means you are comparing your item with 40. If your item is greater than this, then save would remain same. Save is pointing to root. Here also save pointing to root. But if your item is greater than, then pointer would become right of root. But if your item is lesser than 40, your pointer will become left of root. Okay. Next, while your pointer is not equal to null, what you have to do, if your item is equal to info of pointer, that means if your item, suppose I want to search for 60, if you get that item 60, in that case, you are saying location is your pointer and parent is your save and you will return. That means in that case, you don't have to insert, you got that item. Otherwise, if your item is not equal to info pointer, it would be the lesser than or greater than. If it is lesser than, pointer would become left of pointer. If it is greater than, pointer would become right of pointer. Okay. So like in this example, if I want to insert 45, so I got the location that PAR, PAR is pointing to 50. So this thing you need to remember. Now next is that I want to insert now. Okay, this is for the insert in binary search tree. This is info part, left and right part. This is the root. Root is pointing to the root node. Okay, now whenever I have to insert, you need some nodes, empty nodes. So that I would be getting from avail. This thing we have already done many times. An item. Item means the item that you want to insert. That is, I want to insert like 45. And the location. So what was the location previously? That was your null. Okay. Now here, first of all, I will call the find procedure. This one, this procedure I will call. So after calling this, you have the location value and the parent value. Like suppose I want to insert 45. So once I will call this, what would be the location? Location would be your null. And what would be parent? Parent would be pointing to your which node? 50 node. Okay. Parent would be pointing to 50 node. Next, if location is not null, then exit. Why? Because that item is already present and I don't want to repeat this thing. So I'm assuming that I'm not duplicating the values in my binary search tree. Suppose 45 was not present. So location is not equal to, location is your null. Like here location was null. So I'm coming here. So first of all, you need to get a node from the available list. So that is same thing. If avail is null, then write overflow. Otherwise, you need to get a new node from the available. Available will become left of avail, or you can say right of avail. And in info of new, I'm putting item. That means I'm storing 45. Location will become your new. That means LOC is pointing to this new item. Left of new is null and right of new is also null. Okay. Now here the case is if parent is null. Now what's the meaning of this? Its meaning is that in your tree there was a single root node and that root node is not equal to 45. Okay, that means your location was null. You didn't get that element but its parent is null. If its parent is null, that means your root will become the new node. Okay, parent is null over here. Okay, location is also null and parent is also null. That means your tree is empty. There is not a single node. Your tree is empty. In that case, your root will become the new node. That means if I want to insert 45, so I will insert 45 because parent was null and the location was null. So this I'm making the root node and root is pointing to this one. Okay, else. Now this is important. Else means your tree was not empty. Parent is having some value. Now I'm going to the previous node, previous slide. Like here, your this parent was pointing to 50. Okay, this is your parent node. Parent was pointing to 50. Now I want to insert 45. So it is very simple. You just compare 45 with 50. If 45 is lesser than 50, you insert that node as the left child of this. But if 45 is any item is greater than 50, you will insert towards the right child. Okay. So right now your 45 is lesser than 50. So the node that you have made, which node we had created the new node, that was your 45. So 45 is coming over here and 50 would be 45 would be the left child of 50. That means in the left of 50 I would add this node that is your new. Okay, so go to this slide next. Okay, you are comparing item with info parent. Item is 45, info parent is 50. 45 is lesser than 50? Yes. Then in left of parent, in left of 50, you are going to store new value. Okay, new means the new node. That new node in which you have stored the 45. So in left of parent, new is being stored. Else set right of parent. Else means if your item is greater than info of parent, In right of parent, you will store new. Okay. Suppose any times for 55 you want to insert. So 55 is greater than 50. In that case, in right of parent, you will store the new value. Okay. So this is the insertion, how to insert in a binary search tree. First, you need to find out the location and the location of its parent by calling find procedure. Next, from the avail, you are taking a node, you are storing all the values within that. And then this is very important and very simple. Like if your item is lesser than info of parent, then you are storing your node as the left child, otherwise as the